Hello class, so this is going to be CSE 5250 Section 2 Week 3. Now, I'm gonna say a few things first. Number one, this is actually gonna be a shorter video than usual, and because of that there won't be a PowerPoint slide at all for this week. And that's because the content I'm gonna show you for OpenMP is actually pretty simple. So that's number one. Number two, I'm gonna do my best to put out one video each week. And that's because I said a few times that there would be follow-up videos for week 1 and week 2, and that hasn't happened, so sorry about that. I'm gonna do my best to have it so that each week has one video. So that's number two. Number three, I also graded your civs. I also graded programming assignment number 0. So that was the civ of Eratosthenes without any multi-threading at all. So it's basically this. For those who haven't submitted your civs yet, please do so as soon as possible. So that's number 3. Number 4, it's going to be more of a follow-up on what's happened between last week and now. So basically last week I went through how we have last week I talked about how we have these multi-core CPUs being made, and the current trend right now being AMD putting out multi-core CPUs, and not just 8-core CPUs, but also 16-core CPUs. So currently the Ryzen 1000 series lineup was like this, and the Ryzen 3000 series lineup was more like this. This introduced the Ryzen 9 that went up to 16 cores. And the Ryzen 5000 series was more or less the same as this, and well, basically the tech news right now is basically this. Yep, we have the 7000 series now. And well, it is way different than the 5000 series. Currently, I'll say this right now. Currently, the only benchmarks available are those from AMD, and those have to be taken with a grain of salt, because we won't know the true performance of these CPUs until independent reviewers are able to test these CPUs for themselves. When we benchmark the stuff of Eratosthenes, we're basically comparing performance between the different parallel versions against the non-parallelized version. So Program 0 is basically the first of several programs that we're going to be making. Programming assignment 0 is basically the first of a few parallel programs. Actually, no. Program 0 is basically without any parallelization at all. The next programming assignment is going to be using OpenMP to make a parallel version of the civ of Eratosthenes. I'll talk more about benchmarks next week. For now, for this short video, I'm going to be talking about this Hello World program that I posted last week. So let's copy that and paste it into Visual Studio. And there are a few extra steps that you need to do if you're using Visual Studio. So basically those steps are, you have to go in and turn on OpenMP support. So it looks like this. Go to Project, Properties, C/C++, under configuration properties, go to language, and you have to turn on OpenMP support. So if this is no, you have to set it to yes. Click OK, and basically you're good to go. So what happens when we run this program now? It's saying hello world 16 times, and that's because I have a 8-core 16-thread CPU on my home computer. So this is how we know that this program is working. Mostly. The Hello World program that I showed to you on Canvas did have one small issue. And it's basically this. Each thread is saying hello world, and then it's doing the end line here. And each thread is basically, each thread is doing this, so you can have one thread saying hello world, and then another thread saying hello world at the same time, before that first thread has a chance to do this inline operation. So that's why we have a situation where we have hello world, and then this is why we have hello world on being said more than once on a few lines, and a few lines having, well, absolutely nothing. But this is an easy fix, and it looks like this. Basically, what we want to do is whatever a thread has to say has to be done unbroken. So this is an easy way of fixing this issue where we had hello world being printed out more than once on each line, and now here we have each thread saying hello world once and then a new line. Basically what we previously had was a race condition. So how do you know? So here's another question. How do you know which thread is which? So how do you know which thread is saying what? We can modify the hello world. We can modify the program like this. First, we have to include omp.h, and then we can modify the hello world program like this. This is the This is going. Right. The next thing I'm gonna type is the function that returns the thread number. So there are 16 threads, and they each have a unique thread number. So it's gonna look like this. Okay, so if I write the program like this, if I write the program like this, I think you're gonna see I think you might see the issue here. But to make sure, there we go. Here's the problem. It's like the problem from earlier where we had. It's like the race condition from earlier. So we have the problem again. So to fix this problem, what we're gonna have to do is not use cout, and instead we're gonna use printf instead. So to fix this problem, we're gonna use printf. So it looks like this. First, I'm gonna copy this operation here. This returns an integer, and that integer is going to be that threads, and that integer is the thread number itself. So I'm gonna store that in another int, so it looks like this. Now I'm gonna do printf. And then %i, and then comma, and then I'm gonna put the thread number in here. Now if I run this program, it should work as intended. Almost, because I forgot the slash n. So let me fix that. Backslash n. Oh yeah, and the exclamation point. Okay, now it works. Hello world from thread number 0, 1, 2, 3, all the way to number 15. So that's the hello world. So that's the multi-threaded hello world program. So how do we translate that to the set of Eratosthenes, where we want to have it so that so let me just pull up the set of Eratosthenes here. Paste that in here. We have right here a maximum of 200, so it'll search for primes up to the number 200. So if I run this as it is right now, it works. But what if we just add a few extra zeros to that? So now we're looking for thread, we're looking for prime numbers up to 2 million. Here it's taking a while because is it working? Did I break it? Give me a minute. Okay, I tried it again, one order of magnitude lower, so instead of 2 million, it's 200,000, and, well, this program doesn't have any way of telling you how long it took to execute, but if you just did it like, if I'm to just run this as it is, come on now, you can see it's taking a while. And then it prints all the prime numbers. So there we go. That's the set of Eratosthenes, single-threaded. So how do we make this multi-threaded? Well, for our purposes, we have to go to the innermost for loop and add this compiler directive. So it looks like this: pragma OMP parallel 4. So this will make this innermost for loop parallel. So if you run it now, it still took a while, but it still works as it did before. So maybe that tells us it's working, but how do you know for sure? Well, first I'm gonna reduce this back down to 200, and I'm gonna add a printf here. So this is to make sure that the program is working. So printf thread number %i detected %i as non-prime, period, backslash n, and then we're gonna have to pass in okay, so I tried to call OMP get thread num, and it's not working because I have to include omp.h. So now we are getting the thread numbers, but now we also have to get, because of how I wrote this, it's basically saying thread number detected current number as non-prime. So all this is to make sure that the program really is multi-threaded. So if I run this, there we go. Thread number 3 detected 44 as non-prime. CSE-5250 detected 84 as non-prime. So what's going on here? Well, behind the scenes, if you think of this innermost for loop as being unraveled, so instead of a for loop you have like 200 separate iterations of the same exact of the for loop, think of the work as being divided amongst all 16 threads as evenly as possible. So, for example, here thread number 0 detected 10, 12, and 14 as non-prime, and here it detected 84, 87, and 90 as non-prime, and that's thread number 6. So yeah, this is how we know that the work really is being divided up among each of the 16 threads. So yeah, that's basically how we make the sieve of Eratosthenes parallel using OpenMP. What this doesn't show is how long it took, and that's because I didn't include any code here to show that the sieve really is. Yeah, basically this program here doesn't have any extra code to show how long it took to compute. How long it took. Yeah, so I have no idea how long. Basically, I have no idea how long it took for the program to compute the primes. And that's why I recommended that your sieve included some way of calculating how long it took to calculate the primes. So that's gonna be it for OpenMP. It's a short video, I know, but that's because it was a bit of a shorter week. So, oh yeah, one other question. Why the innermost for loop? And can't we just why the innermost for loop and not the outermost for loop? Well, let's try it and see what happens. Well, let's copy that and paste it into Notepad and see what's up. Let's find. Let's put in 200 as non-prime. Let's go through the list and see what's going on. Well, basically, what's going on here is what's going on is this. If I made the outermost loop parallel, the inner loop is going to be repeated for all 16 threads instead of so basically what I'm trying to say is, if I made the outermost loop parallel, it's gonna be repeating the same job 16 times, once for each thread. If I made the inner loop parallel, it's going to properly divide the work among all 16 threads. So that's why we had to make the outer loop not parallel, but instead the inner loop parallel. So that's gonna be it for this week's video. Yeah, it's a little short, but yeah. Making a parallel for loop really is that simple. Though there are a few more considerations that we may need to keep in mind for other programs, because back in operating systems, you may have heard of the idea of a critical section. Here it's a non-issue because we have threads. We have each thread writing to a unique position in here. And there is no problem because for our case, there is basically no problem of one thread writing to the same place as another thread because they're writing basically the same thing. And they're writing in unique places. So here it's a non-issue. If we had a problem where I'll explain a little bit more of the technical things that could happen when you have critical sections, possibly next week. I know that week is supposed to be on NVIDIA CUDA, but because of what's been going on my end, basically I had problems with my car, so because of that everything's gonna be shifted a little bit further back. Yeah. That's gonna be it for OpenMP. Next week I'll explain a little bit more about the technical stuff on what happens if you have, for example, a critical section in a program. Here as I said, we don't have critical sections to deal with, but you may have programs later on that does have critical sections. So I'll explain more about that next week. So for now, I'm just gonna end off this short week 3 video, and later on this week I'm gonna have a submission box for. Later on this week I should have a submission box for what's going to be program 1, and that's a parallel set of Eratosthenes using OpenMP. For those who are using C++ for your programs, you can basically more or less follow these instructions and you're basically good to go. For those who are using Python, you're gonna need a different set of instructions because, well, the ultimate goal of this first program is to make a multi-threaded set of Eratosthenes. It doesn't matter if you're using OpenMP. Rather, that's just one way of making a multi-threaded program for C++. If you're using Python, you're gonna have different instructions for that. So next week as well, I should have instructions for using Python. For those who are using different languages that isn't C++ or Python, maybe consider switching over to C++ or Python. So that's going to be it for OpenMP. For those using Python, stay tuned. Hopefully I'll have additional instructions for those who are using Python. Alright, so that's going to be it for this week. I'll see you next week. If you have any questions, feel free to email me. So, alright, that's it.